Hello, welcome to final unit of Calculus and Vectors. We are in Unit 4, and it is Applications of Derivatives. So Unit 3, we did all the background work. We've learned all the base skills. We are now not going to learn anything new about derivatives. We're just going to look at how to use them. That's basically what we're doing this entire unit is applications. So our first lesson today is curve sketching. So today's goal, I can recognize the components necessary to successfully sketch a function. With this lesson, usually I would just I'd ask the question, and you would tell me all the things that are necessary to be successful when it comes to sketching a function based on your grade 12 course from last semester and any of the previous knowledge that you've had before. So a lot of these screens are already pre-done. Basically, you can pause it, copy out the screen because there's no errors, and then you can listen to the discussion that goes on. So first thing I always ask you in a classroom setting, I'd say, what are the requirements? What's necessary to graph or sketch a function? So first thing you learned back in grade 9 is the x and y intercepts. So that's one of the components. Grade 10 and grade 11, you get introduced to max mins. So yes, you need to know where the max mins are located. And then after the max mins, grade 12, the advanced functions course, they teach you the location of vertical and horizontal asymptotes. We're going to revisit that because the horizontal, we've got a more efficient way to do it. Domain and range, that is a grade 11 skill. End behavior. End behavior is how does the graph act at the ends of the asymptotes. You talked about that in the advanced functions, and now we're going to clean that up a little bit in this particular course. Inflection points. So there's a terminology that may be new. Hopefully you had a chance to talk about this last semester, but we will talk about inflection points, and then this might be something that's completely new, and that's concavity. So those are really the seven key factors I feel in order to successfully graph a function greater than a polynomial, so cubic or greater, or a rational function. So let's look at the xy intercepts. I'm not going to drag this out. So again, you can pause and copy the note itself. There's examples there, but fairly self-explanatory. If you want to find the x-intercept, same as it always has been, you let y, or the function f of x equals 0, solve for x. So the example I have here for you is a rational function. With a rational function, if you let y equals 0, you're basically just setting the numerator equal to 0 and solving. So that's basically with a rational function. If it's a polynomial, you're just setting the polynomial equal to 0 and solving. For the y-intercept, if you want to find the y-intercept, you let the value of x equals 0 in the equation and solve for y. And it's always the easier to do because you're just plugging in. All the x's become zeros or get canceled out. And you're basically finding a value for the y-intercept. All right, and because we're dealing with functions, there's only one particular y-intercept for our function. All right, now just going back here, and I'll add this in. Didn't really finish this part of the note. So if you're setting the numerator equal to 0, that would mean 0 equals x squared plus x. Factor out the x, you'd have x plus 1. So therefore, the values of x would be 0 and negative 1. So those are your x-intercepts, so that's where the graph crosses the x-axis. All right, crosses x-axis. Okay, so there's your x and y intercepts. So same as they were in grade 9, it's just the functions look a little bit more complicated. Max min. How do you find max min value? Well, again, I'm going to go through and look at the whole note. And what I'm going to do, let's just look at how you used to do it. So this is what you had to do in grade 10 and grade 11. So we would start you off with quadratic formula or quadratic equation. To find a max min, you had to complete the square. So you're looking for what You divide 6 by 2 and square it, so 6 divided by 2 is 3, and that's how I got the 9. That first group of terms now create a perfect square. All right. Then from there, we end up with our vertex, and our vertex was -3, -19, and we get that from your P and Q, or H and K, depending which system you came from. Are you going to have to complete the square this year? Absolutely not, because we have a better method in order to find max min. Okay. If you look at the picture here, up at the top, for a parabola, what do you know about the vertex? The vertex is the point where the slope of that tangent line changes to a positive slope. Whoops. I was hoping I could draw while that circle is there. Apparently not. But the location of the vertex is where the slope of the tangent line is 0. Okay? So what I wanted to do, here we have a negative slope. It decreases as you move closer. Once you get to the vertex, it's a 0 slope, and now it switches to a positive slope. So at the vertex, so I'll put that right here, at vertex, slope of tangent is 0. So slope of tangent is 0. All right. So what that means then is that if we take the original function, so if you look, I just took the function that I used over there from the example, and we just take the derivative, so y prime equals 2x plus 6. I know that the derivative is just the slope of a tangent. We talked about that. And now I know that if I set it equal to 0, I'm going to find the location of the vertex. So set the equation equal to 0, and I'm going to solve for x. And we find that x is equal to -3. And if you check over here, you find it's the same value. I plug -3 into the original equation. So plug x into original equation. And now I come out with my y-intercept, which is the same as what we had over there. So now we found the min or maximum using derivatives. So you don't have to complete the square anymore. We're simply just taking the derivative and setting it equal to 0. Now that's for a parabola. What happens when we're dealing with all polynomials? So for functions other than quadratics, okay, let's just get rid of this whole thing. So I'll give you a second to absorb. The first one, we have a quartic. Okay, guess what? Everywhere there's a max min, you can think of it as being like a vertex. The slope is 0 at those points. So if we take the derivative of our quartic and set it equal to 0, we'll find the location. All right. If we have something looks like this with a slant asymptote, it'll still find where the slope is 0. Okay, so any function you can kind of sketch up that has a max min, you can then determine where it occurs. So in my red box here, max min values always occur when that y prime or f of x prime, so the derivative, is equal to 0. So max min points are also called critical values. All right. So critical values are used in the textbook, and you'll hear professors talk about critical values. Max mins fall under that category. They're one type of critical value. All right. So how do you determine if it's a max or a min? All right. How do you determine if it's a max or a min? So this is kind of a separate note down here. So if you want to just divide that off. The bottom part here answers a different question. So how do you know if it's a max or how do you know if it's a min? If you can look at the equation and determine that it opens up or down from the equation, then you're okay. Because remember, you're not going to be given the graphs. You're not going to have this graph and say find the max min. All right, you got to go from the equation. So let's start with a parabola. So here's the parabola, and we did this in Unit 3 when we were introducing ourselves to derivatives. Here's the parabola. There's where the slope is 0. All right. If you take the derivative and graph a parabola that opens up, you end up with a positive slope. Okay. If you take the derivative of that positive slope, the second derivative is a positive value. So from that, if you find y double prime and input the critical point, so the vertex that you found, or location of max min, you get this table right here. All right. And this is something that will need to go on your cheat sheet for graphing. If the second derivative is positive, so it's greater than 0, a min occurs. So we have the situation we're talking about over here. This is a min value for the parabola. If it is a negative value, then you have a max occurring, so it's less than 0. Okay? So this is how you determine whether you have a maximum or minimum value. And there's going to be some people here that are saying, well, what happens, what if the second derivative is equal to 0? Okay, we're going to deal with that later on. So later in lesson. So just be patient. All right. So that's the answer later in the lesson. All right. So there we go. Okay, vertical and horizontal asymptotes. So vertical and horizontal asymptotes. So I do them side by side here. So vertical, same as it was in the grade 11 course that you took, the 3U. You set the denominators equal to 0, and it's basically your restrictions. So you state your restrictions. So my example here, asymptotes come from the denominator. So what are the restrictions? I'm going to end up with vertical asymptotes at 0 and -1. So vertical asymptotes come from our restrictions. All right. Horizontal asymptotes. This is where we take the limit as the function approaches infinity. Oops. So as it approaches infinity. All right, so we are really doing the limit of our function. So the limit as x approaches infinity for f of x. That's what we're doing. And this is the process that we talked about in Unit 3. All right, so from Unit 3. So from Unit 3, you find the largest power in the expression. You divide through every term by it, and that's what I'm doing here. So every term is being divided by x squared. So exactly the same as it was in Unit 3. And we find that the limit as this function goes to infinity is 5/2. So therefore, a horizontal asymptote at y equals 5/2. All right. So those are the first couple of points dealing with the curve sketching. So I'm going to have to sum this up in a second video.